that more or less? So now we're going to different failure mode. So first is the bending failure. So bending failure is basically you can have the inertial load from the structure. Another, so that is the inertial load from the structure. This you can get from this response spectrum method. You then get the inertial load. Then you find out the load on each pile. That will give you the inertial load on the pile head. Second is if the soil flows, you get the lateral load, right? So they are the two bending. So these two will cause bending in the pile. Yeah? And how to analyze them? There are different approaches to analyze this problem. You can use a subgrade modulus approach. So those who are using deformation, so what we will see is that we have some example on this one. Second approach is a continuum approach. You model the whole thing in a finite element. So you would have to use a 3D finite element, Plaxis, model the whole thing. It's very expensive in terms of time, in terms of knowledge what you need. It is rarely used for routine design. You use these things for a very complex problem, so you will not normally use this approach. So these are used to validate something, a very, very complicated problem, they use that. But the one which is used is this one. And this is known as beam on nonlinear wing-clef formation. So what it means that you model the pile-soil interaction by a set of springs. These springs are modeling the interaction of the pile and the soil. Now, can somebody tell me the reality is this and modeling like that? What's the difference? Why? What are things we are not? If you model this problem by this, what does it mean? So what is it? What we are not considering here? Damping. This is very complicated. Yeah, fine. Good. Damping. So yeah. Soil is uniform, but we can say, for example, this part of soil is very strong. I can make this spring very stiff. Right? Something we are not considering.
Confinement? Confinement? Is it the confinement?
Confinement. Okay. So if the soil is confined, so that means that and confined so means that the movement will be small, isn't it? So I can make this spring stiff to take it back on that. Okay, think of this as a sofa. In a sofa, when you sit, so there's a continuous thing, isn't it? Except I will have no sofa. I want some springs. See what I mean? So these springs don't talk to one another. They are individual springs. In reality, it's a continuous, right? So that's one thing. So what we are doing, we are trying to model a sofa by discrete springs. I think I just say. So that's the sort of, if you see the sort of analogy is that. Okay, but this can be solved. This is the one used in practice and used everywhere, right? So things are being calibrated so that they give same answer more or less, right? And if you see, this is known as PY method. If you look in literature, PY method. PY is just, this spring is known as PY spring. P is the pressure, Y is the displacement, right? So this is known as PY method or PY spring. That is the most widely used approach to model pipe soil interaction, right? In terms of codal provisions, what does the code say? How to take into account the lateral load? If you look at the Japanese code of practice, what they are saying is that you suppose you have got a non-liquefied crust, meaning, say, normal condition for a soil to liquefy, there must be water, isn't it? If there is no water, it won't liquefy. Therefore, important part is that where is the water table? In a river bed, the whole thing can liquefy, but in normal ground, you will have a non-liquefied crust, because if the water table is here, this part will liquefy, this will not liquefy. So, if this thing liquefies and wants to flow, that it will take the top with it, right? So to compute the forces, the Japanese code says you find out the passive pressure. So this crust will give a passive earth pressure, and you take into account the lateral load on the liquefiable layer by 30% of overburden pressure. That means, suppose here the overburden pressure is say 100 kPa, the lateral load will be 30 kPa. So it's basically you find out the equivalent pressure and you can find out the force on the pipe. So what does that moving soil apply pressure on the pipe? Okay? To be clear. Overburden pressure is the total vertical stress. So total vertical stress, that means total, not effective. So total overburden pressure. So basically, what is the vertical stress there? Right? Not effective. If we look into the Eurocode 8, so Eurocode 8 will tell you that liquefiable zone should be neglected for lateral resistance. That means the liquefiable zone, it doesn't give you any lateral resistance. The important part is to find out which layers will liquefy. Yeah? And then you can make lots of assumptions, scenario-based design, right? And then it says to do like a plastic hinge if there is a location of stiffness contrast. Say for example, it's going through a layered soil. We found out a soft soil and then a strong soil. So that in this intersection will be having a higher bending moment. So it asks to design like a plastic hinge so that it can deform a bit more. Right? So if you look into the other codes of practice, effectively what we are seeing, all these codes of practice are suggesting only bending mechanism. They're actually taking account the bending mechanism, so the lateral load. This is again a US FEMA code. Again, they are saying that you take into account the inertia force. So that's from Nihart code. This is the US code. So if you see here what it is saying, that pipe without building, that is the inertial building, this is the building inertial load, and then you also apply from the soil. Again, the main thing is the lateral load acting on the pile due to inertia or down movement. Now, here's the thing where the code can't explain all the mechanisms, and codes takes time to get updated, because to update a code, there will be a committee, code committee, a lot of people sit together, find a common ground, so it takes time, right? So I'll show you where the code doesn't take it account. Now, here is two particular buildings. So what you can see is that here's this building, is another building. In this case, so the building is intact, but both of them move. In one case, this is sloping down, this is a level ground. The main point to state is that in one case you had no lateral spreading, so there is no ground flow. The ground didn't push. In this case it did, but you see similar failure. Right? Another example is this particular shore bridge. Now this bridge I've given in the your coursework factor. It's a very interesting bridge. This is a new bridge, only 2 months old. Steel pile. So if it's steel pile, you can imagine that actually there is good quality control. Because if you do a concrete pile, there are issues with the quality control, and you can have a non-uniform stiffness things. A steel pile, and after the earthquake, the bridge failed in this particular way. But the thing is that the current code, they all say to design against the lateral flow of soil. That's the main cause of failure. But if the bridge, if that's the cause of failure, would you not expect that the piles here would fail? Because you have a lateral flow there more. Because the bridge middle is more or less flat. Because the bridge is the river, the middle of the river will have a flat surface, right? So you expect that these things would fail first. But this didn't fail. Also, if you see, if the flow was in that direction, this pile should have failed in the other way. Right? So that means the way how we design it, that's against bending failure still now, doesn't capture all the mechanisms that happens during earthquake. Right? So what I have done over the years, I've studied this particular bridge. What I found out that this bridge failed in 1964. The code was revised 4 times. So I checked the bridge against the current code of practice. It was safe by 1.84. So if you found out that it's still safe, so it means that we did the design using the wrong mechanism. So what governs is not this mechanism. Right. So let's come to buckling failure, which the codes not yet considered yet. Now, if you look into piles, the piles can be as long as 170 meters. If you look into this particular bridge in Bangladesh, these piles were 170 meters long. So piles can be very, very long. So Oxford piles are 80 meters long. They are very, very long. Right? And so if the pile is, if one soil liquefies, so here is the spring approach that we all use for design. that's the currently all the approach. If you look into routine design, they will use this spring approach. The reason being, through the spring approach, you can model the soil layering. If you have a soil that is say clay, then sand, then stiff sand, then clay, etc., etc., you can all model by having different springs. Okay. Now, if soil liquefies, so this part you will have no springs, because what we're saying is that it does not have any support. So therefore, a vertical load, it will be completely unsupported. Right? Not only that, due to friction, this load reduces. What I mean to say is here is this. Suppose you apply a load at the top, say you apply a load of say 700 kilonewton of load, and that's the ground level here. So if I draw the force along the depth. At the top, what would I see? If I have a load cell to record the loads, what I will see? 700. What I would see here? Less or more? More or less?
Yes.
Because this friction acts of, if you look at this friction, what it's doing is taking the load off, isn't it? Yeah? If I take a section here, the load will be 700. The friction here, the load will be 700 minus x. Where x is the friction, isn't it? Yeah, it will reduce. Yeah? So you see that the load will reduce, and towards the base, you don't see much load. Yeah? So what happens in this case? When it liquefies, so the load was earlier like that. As it liquefies, say soil up to a liquefies, the load becomes straight, doesn't it? And then it starts to reduce. Yeah? Because you don't have any friction here as well. Yeah? You see what I mean? Load was just 700, then it reduces as you go down. But when soil liquefies, you lost all this friction, right? And you suddenly see a big change in the axial stress, right? So in your coursework, will come in use. If you know the liquefiable layer, what will happen there? So you know the vertical load of the pile, and you can change this, and you can see the change in stress distribution as well liquefies.
That location be the location of the water table.
Water table is what table? What do you mean?
Because you said that's the layer that liquefies. So how do you know where it liquefies to?
Then you can calculate. What I've taught in the second lecture, the depth of liquefaction. So how do you calculate depth of liquefaction? So you can see what depth it liquefies. Okay. Yeah. So here's the model about no liquefaction. So full support. When soil liquefies, you have to ignore this layer, right? And and this becomes a model. Just to compare the difference, so currently all the codes, they ask you to design for bending, unilateral loads. If you see what happens, it says you apply a load and see how it deforms. But you can get a similar deformation pattern if you simply have very thin needles and at the top you put some loads. Yeah, the same thing, isn't it? So you can see in both cases it moves sideways. So now you remember the picture I showed, one sloping down, one level down. See, it doesn't matter. You can have a similar deformation pattern by two different mechanisms. And if you want to work out a buckling load, how will you do? So you can use this simplified equation, isn't it? Pi squared by L effective squared, right? And once you know the unsupported length, and you know the boundary condition of top and bottom, you can use the appropriate effective length, and you can compute the buckling load. So therefore, for a new design, if you know that what part of the soil would liquefy, you need to consider that length and find out if that liquefies, what is the buckling load. So axial load should not exceed that. Yeah? And in some cases you may want to have the ground improved so that it doesn't liquefy to that depth, and then you can take it from there. Yeah? Again, if you look into in ATI or Eurocode, they don't consider yet buckling in liquefied soil. So what they say is that if you are driving in soft soil, you have to take into account buckling in an extremely soft soil or there's high lateral load, but it doesn't say about liquefied soil. That's excluded. So here is the different boundary condition for different cases. So you can have a case where a building is there, you have a pile resting in a non-liquefiable dense layer very deep. This part liquefies, here is non-liquefied crust. In this case, if it is embedded deep in a dense layer, we can consider it to be sort of fixed somewhere there. So that it will buckle in this particular pattern. But it seldom happens, because if it is liquefied soil, this thing will move on top of it, right? You really can't have a top fixity. If you have a case like that, it's not very well embedded at down deep here, right? The pile would buckle in that particular way. So you know the effective length would be, you know how to find out the effective length. This would be 2L. This case, this one is L. Okay, so the main thing is we assume that the pile in the liquefiable layer is unsupported, right? And then the fixity at the below, at bottom and top. At the bottom fixity, we assume that if it's embedded more than 5D, then you can assume it's fixed because it's going down. If it is not, it will pin. The top one, if the building is rigid and it is basically rigidly connected to the pile cap, the top part can only translate but can't rotate. If you have a single layer of piles, then the top part can rotate. Yeah, and depending on this you can get the different boundary conditions, and you can compute the buckling load for pi. Yeah. For you, it can be hard because this is a structure building concept. This is more about how do you find out at what load a thing would buckle. Okay. So you have to look into some column design K6 is the shore bridge pipe.
How do you define a fixed end? Basically, like how deep does the pole have to go to be fixed?
Okay. So to get fixity 5 times diameter.
5 times.
So you have to take into account the 5 times diameter. So if it is embedded 5 diameter below,
And if it's like
then
partial, like in between the two, would you say?
then you use your judgment, or do you say, okay, if you spend this, fix this, but then you go to 5 diameter. You see what I mean? When you go to 5 diameter or this numerical, when hand calculation won't give you the number. They try to model it more mathematically to see.
This is like, it'd be elastic. This is the Euler.
Oil, yes. It's oil and
yeah.
buckling.
So, isn't this like a perfect? This is with like no imperfection.
Yes.
No eccentricity.
That's why you have to get your safety of 3 or 4.
Okay.
Yeah? Yes. So, this is for a stress-free vertical, all those assumptions that is the vertical load is purely vertical, and no stresses, no insufficient stress. But reality, you will have the safety of 3. And this is what happens in most cases, because if it's liquefied, suddenly see the buckling unit is dropped.
But like adding this though, aren't you like making the foundations like astronomically like huge? Like they become-
Now, if you look into which buildings survive the earthquakes, you see the piles, what piles are. And then you see what you would need instead of small diameter many piles, they need one large diameter.
Is that why they do the performance based because they can't sometimes make that cost?
So you don't go for many small diameter piles, you go for one large diameter. Yes. So exactly the number 6 is the shore bridge example. We look at the shore bridge example. The shore bridge as shown you before. So look into
That's not
this one.
basically the less slender.
That's the case. Single pipe. See, row of pipes, row of single pipes. That is that particular case. Yeah. See, it's a row of single pipe. The pipe was the pipe is deformed in this way. So this pipe actually after earthquake deformed in that particular way.
When you said about using like large diameter pile to help with the buckling, what diameter would you count as large? Like,
Depends on the depth of liquefaction.
okay.
So I would say as thumb rule, if you see that the depth requires to 10 meter, probably 10 by 12. So around, you know short term, long term. How do you design a long term, or how do you short term? So how do you do a stratagram design? You normally do unsupported length
Yeah.
by 12, isn't it? Yeah. It's exactly similar.
Okay.
Same thing.
Oh yeah, yeah, I get you.
So you do, isn't it? You for a current design, how do you start? So I will do length by 12.
Yeah.
Yeah. Okay, so if you look into, here is the example. Actually, here are 15 cases of different piles, pile supported structures from different earthquakes some building, some oil tanks, bridges, etc., etc. Here what we are doing, we are plotting the effective length and our minimum. Because effective length, why? Because to normalize the length, because of we could do it here, the liquefiable zone, but that's not accurate because piles can have a different effective length. And our minimum, because we had some are square pile, some rectangular piles, some are circular piles, hollow piles, so you can normalize the R minimum. And this plot shows which one was good, which one was poor performance. And what this graph shows, actually, the piles that fail, they're all long terms. So that means, though the codes of practice say design for bending mechanism, that doesn't govern the design. The design is governed by buckling mechanism. Yeah? Many of you may have seen this graph, isn't it? This Euler ranking, yeah? So you can see this is slightly structural engineering. Anyway, so the main thing is that for a concrete structure, for a concrete, you will see you have a yield strength. So that means that the stress at which it crushes. So it will crush. That is that line. So that means if the axial load is high, at a certain stress it will crush. So this one is a no-go zone. You will have the failure material. And this one is the perfect color. What you are saying? The Euler formula. And actually things fail in between. So this graph, this green line, mediates strength to stiffness. So that's basically a stiffness issue. So it buckles. So again, that graph shows that actually buckling was governing those pile designs. And also, this was shown by an experiment that actually things do buckle. And again, then we can look back in many of those case studies to show that actually what the pile that failed had safety of less than 1 against buckling. So actually, it's the buckling that governs the pile design in liquefiable zones. Okay, now how do you then combine this buckling and bending analysis? So, if you want to do the work we can do the work in few different ways. One is, say you find out that actually you have got water and liquefiable soil, this is liquefied. So from your simple calculations, you can find out the depth liquefaction. So you find out that is liquefiable layer. So first thing for any analysis, you find out, draw a diagram like this. Very simplified diagram. It will tell you the pile, dimensions about non-liquefiable layer, liquefiable layer, and whatever. And then scenario 1, the liquefied soil can flow. Right? So you apply the force. You remember the Japanese code that you apply 30% of the pressure. So that will give you a force here, force there. You can analyze this by hand, right? This is the limiting pressure method. So you can apply your pressure. So here's the model how you can analyze. Because at the end of the day, you have to find out the bending moment and find out the reinforcement or the pile section. So you have to compute the bending moment. So here is the model you can use to compute the bending moment by a force-based method. So you apply the force, but remember to have the vertical load here. Right? The code doesn't say put the vertical load there. It doesn't say explicitly put the vertical load there. That was the main reason people didn't consider it. And they had a small section. Right? When you start putting the vertical load there, you see that the pipe has to have a large section. Right? Second is, if you can find out the ground deformation, in some cases people have found out actually the ground will deform. So that means in liquefied soil, after earthquake, you see that the ground moves that way. So you can achieve a distribution, and you can apply some movement at the top. This is another way of modeling the whole problem, right? Because in some cases, there are empirical ways to calculate how much a ground would move that way. So you can use the top movement, achieve a distribution, and you can push the ground to show how it will, what's the pipe bending moment and deflection. Right? So you're giving a displacement, the whole problem. Right? This is like a sort of, like a pushover type analysis. Now, what happens in this case? Just to see the effect of axial load. Now, if the ground moves laterally, and I am plotting here the delta soil, means the ground movement and the pipe head movement, right? If I don't apply any vertical load, suppose there is no vertical load. Suppose I don't apply vertical load, I only give a lateral load. Means the ground movement. Suppose the ground moves, so the pipe will start to move with it. But after a while, the ground would move, the pipe would stay same. Say you have got a pipe here, and a slope is moving. Slope will